In this video, I will briefly go through the history of modern science, and by that I mean the last 500 years. As a Dane, I will take the liberty to just point out a handful of Danish scientists on the way, while covering the most major discoveries which we will cover later and then discuss in more detail. So let's turn the clock back to the 16th century. Galileo Galilei was an Italian scientist who invented several things. Although he did not invent the telescope himself, he was the first one who used it systematically in astronomy, and with the help of his telescopes he concluded that the moon was not smooth and perfect as thought earlier. He also used them to discover the four moons of Jupiter, making it the first time moons were discovered to orbit other planets than Earth. He was also famous for his experiments at the Tower of Pisa, where he studied how objects fall to the ground. His studies of falling objects led him to conclude that all objects fall equally, no matter their masses, which is indeed correct if you don't have any drag from the air. Around the same time, the German scientist Johannes Kepler, who studied the work of Danish astronomer Tycho Brahe, formulated the laws bearing his name in the early 17th century, namely the Kepler's laws, which describes planetary orbits. His work was, however, largely ignored initially until Newton derived Kepler's laws from his law of universal gravitation. Going forward, Isaac Newton is probably one of the most famous and well known scientists in physics. He not only derived Newton's three laws of motion, describing how forces act on objects, but he also invented calculus, which is part of the mathematics that is essential for probably most physics today. As I mentioned earlier, he derived the universal law of gravitation, which describes the gravitational force between two bodies with mass m1 and m2, and with this he could derive the planetary motion of our solar system with great accuracy, where g is the gravitational constant and r is the radius. Around the same time, Danish scientist Ole Rømer observed the movement of Jupiter's moon Io, and from these observations the first calculation of the speed of light was achieved. Elsewhere in Europe, thermodynamics was heavily explored, leading to new types of engines, and in particular the steam engines. And a basic form of what we now know as the ideal gas law was formulated as a result of several of scientists' work. We denote P as the pressure, V as the volume, N the amount of substance, R is the ideal gas law constant, and T is just the temperature. Thermodynamics was a topic which received much attention in the 18th century with a lot of trial and error. At the same time, two Swiss scientists, Daniel Bernoulli and Leonhard Euler, made significant discoveries in math and physics. Bernoulli is especially known for his work in fluid mechanics, giving name to the Bernoulli's principle, which is a conservation law important for airplane wing design. Euler is very known for his contributions to math, and one will find his name associated with several of equations. An interesting thing to note is that the discovery of Euler's number E is actually accredited to Bernoulli and not Euler, but because Euler introduced the number as E in his work, this later became the standard symbol. The 19th century continued with more inventions, and the first electric battery was invented by Italian scientist Alessandro Volta. Inspired by this invention, Danish scientist Hans Christian Ørsted later discovered that electricity and magnetism interacted with each other, thus discovering electromagnetism. As we will discuss later, the electromagnetic force is now understood as one of the fundamental forces in the Standard Model, and since gravity is currently not understood fundamentally and hence not in the Standard Model, it means that the electromagnetic force was the first of the fundamental forces to be discovered. Following this, the English scientist Michael Faraday contributed significantly to electrodynamics and paved the way for electric motors and generators. Shortly after, German scientist George Ohm introduced Ohm's law, where I is equal to V over R, which most high school students will have come across in physics, where I is the current, V is the voltage, and R is the resistance. Many other discoveries was made around this time, including the discovery of the Doppler effect, which explains why the sound coming from an ambulance approaching you is different from the sound when it's going away from you. Thermodynamics reached a significant milestone, greatly helped by Lord Kelvin, who became the first to correctly determine the value of absolute zero at minus 273 degrees Celsius, or 0 degrees Kelvin using the unit named in his honor. He also helped formulating the first and second law of thermodynamics: delta U is equal to Q minus W, and delta Q is equal to TdS, where delta U is the change in internal energy, Q is the heat energy, hence delta Q is the change in heat energy. W is the work done by the system, T is the temperature, and ds is the infinitesimal change in the entropy. In the latter part of the 19th century, Scottish James Clerk Maxwell made further progress in the field of electrodynamics by showing that the electric and magnetic fields are propagated through space at the speed of light. Furthermore, he showed that visible light is just one of many types of electromagnetic radiation, and the only difference is the frequency and the wavelength. Thus, the wave theory of light was very well supported. Since the days of Newton, the question had always been if light should be described as a particle or as a wave, but with Maxwell, the wave picture gained popularity. Before discussing the 20th century, let's just do a quick recap. At this point, classical or Newtonian mechanics could solve very complicated problems, and thermodynamics and other topics were very well established. Due to all this success, it was thought that most of this important physics was already discovered and only minor work was left to do in physics. The inconsistencies of the theories were ascribed to minor issues that could be fixed fairly easily, or they thought so. Needless to say, this picture of an almost complete understanding of physics didn't survive long in the 20th century. In the last years of the 19th century, Wilhelm Röntgen discovered X-rays, and shortly after it was discovered that some matter emit a radiation. In 1897, J.J. Thomson discovered the first fundamental particle, the electron. Not long after did Marie and Pierre Curie coin the term radioactivity. The atom, which was previously thought to be indestructible, was now found to disintegrate on its own in some cases. Shortly after, both beta and alpha radiation were discovered, leading to the idea that the atom consisted of a positively charged nucleus and a negatively charged electron, a model of the atom that would be unstable according to classical theories. The proposed ether which light should propagate in was not found, and classical theory was found to be full of shortcomings already around 1910. The study of the atom continued and later led to the nuclear physics that was pioneered in the 1930s with nuclear fission. In the meantime, German Albert Einstein had postulated his theory of special relativity in 1905, which revolutionized science and fixed the shortcomings of the ether, which was never found. This theory stated that the speed of light in vacuum is the same for all, and the laws of physics are the same for all initial reference frames. This led to the fact that the speed of light is the maximum speed of any physical object, and it led to the very famous mass-energy equivalence relation E equal to mc squared, where m is the mass and c is the speed of light. In 1915, Einstein had developed the theory of general relativity, which brought new physics with it, like light bending and gravitational time dilation, which means gravity can affect the speed of a clock, which was later confirmed experimentally. This theory also fixed the error in the Newtonian calculation of the orbit of Mercury. General relativity is now fundamental in the study of cosmology. Around the same time, Russian scientist Alexander Friedmann pioneered the idea of an expanded universe and derived the Friedmann equations, which describe the expansion of space, which the American astronomer Edwin Hubble's measurement supported. In combination with Einstein's field equation from general relativity, these discoveries have led to the Standard Model of cosmology, not to be confused with the Standard Model of particle physics. As the new theories of relativity of Einstein sent shock waves through the world of physics, German physicist Max Planck discovered that electromagnetic waves were quantized with energy E. The energy is equal to h nu, where h is Planck's constant and nu is the frequency. This formed the foundation of quantum mechanics, which Danish physicist Niels Bohr helped to develop, and he came up with the Bohr model, which is the description of the atomic structure, which is used in most chemistry and physics classes at high school level. It is a simplified model of a more realistic model, but is nevertheless very useful. Quantum mechanics finally solved the nature of light. As it turns out, it's not just a particle or a wave, it's a combination of the two, which is called a wave function. Therefore, light sometimes seems to behave like a particle, and in other cases it behaves like a wave. German physicist Werner Heisenberg discovered the fundamental uncertainty built into physics, which we now know as the uncertainty principle. This is a very important feature of quantum mechanics. It was also around this time that Erwin Schrödinger developed the very famous Schrödinger equation, which we will not discuss further now. At this point, we are around 1930, thus just 30 years after the classical world of physics has been superseded with the new theories of quantum mechanics and relativity. The English physicist Paul Dirac continued to pursue a relativistic quantum theory, thus combining quantum mechanics and relativity. Such theories are now generally called quantum field theories. After the Second World War, the field became well established, and the American physicist Richard Feynman developed new essential math for this field and came up with the Feynman diagrams for describing fundamental processes, something which we will discuss later. This framework is still used today, and it is describing the interaction of fundamental particles. In the middle of the 20th century, a new sort of panic arose. The initial idea of having a world of atoms made from electrons, protons, and neutrons had also been ruined, as many other particles was now discovered. Order was finally restored with a standard model of particles, which neatly accounted for the discoveries of the new particles and explained key fundamental processes. And at this point, we are more or less back to today. Of course, I know I have left many important things out and not mentioned several of scientists who deserve to be mentioned, but to cover everything would take too long, so feel free to comment on which important ones I have missed and should have mentioned. Otherwise, I hope you have learned something new and found this somewhat interesting. Having covered this brief history of physics, it's now time to jump into the physics in the next video, so stay tuned for the next one.